With several X's in play, we also face a new challenge compared to last week, and that's the model selection challenge. The fact that now we could maybe start playing around with a number of different models. First, very rapidly, that to discussion about that there are many ways to actually do this. And the first way I share with you is something that we do not otherwise talk about in the eNote, in the book, is that we could build models up from the bottom up. And in a way, starting with maybe only temperature in the wind, and then temperature in the wind, what the heck does that mean? Temperature in the model, and then add the wind, and then finally add the radiation, and sort of check each model and see, is it really necessary to have those in my model? That is a forward selection procedure that some people would choose sometimes. It's perfectly valid approach. We will, not to make it too complicated, focus mostly on the backward approach, which is a really nice approach when we have information enough for doing it. And so for that is actually the idea is to start with a full model, whatever that could be. That can maybe be challenging sometimes to decide, but we sort of start with the largest possible model in the situation we're in. And then we look at whether we really need all the X inputs. And then if we really don't need an X input, if it's non-significant, I will throw it away again, step by step. That's kind of what we mean by model reduction or backward model selection, starting with a big model and then reducing it to not having a too complicated model, following, some call it the Occam's razor principle of we shouldn't have a more complex model than actually supported by the data at hand. For instance, and now we should soon go and have a look in R again. For instance, I could begin with this full model where I include temperature, wind, and radiation, and then for the fun of it, I also include a noise variable. And then let's see what happens. And let's see, maybe I'll skip the noise part just to let you have a good break also. Let's see. We also need to do it here. So do I have the noise in there now? Let's just check. I do have a noise, so that's fine. I can do the noise. So here, let's see, here we have here, I do the backward selection. I would, and this is the first time we do it actually here, so look at the resemblance to, maybe if I didn't say it explicitly, here it is, then the resemblance to last week. It's basically the same LM function. I'm just putting all the inputs plus the 1 plus x2 plus x3. I'm just adding all the x inputs in the model expression in the LM function. That's the way to make R do the multiple linear regression fit for us, right? And you get an output which is basically like last week. The only difference would be that the coefficient table is extended with a row for each of the x inputs, right? Otherwise, of same structure as last week. Then, if I should follow my backward elimination, backward model reduction technique, I would look at all of these 4 possible X inputs, and then I will see, is there any one of them non-significant? And if there are more non-significant, which one is this non-significant with the largest p-value? In a way, the least significant if you want, right? In this case, it's the noise. So the principle would tell me, throw out the noise of the model, it doesn't help you with anything, so I don't need it, take it out of the model, right? That would be the principle. And I would go to the next level, and I would try to, I'm here. Whoa. I'm struggling with this here. Here we are. Look at this. So basically I removed the noise from my model expression, right? this artificial variable, just to show you that that could happen. Then I have my MLR with temperature, wind, and radiation, and they are all significant, so I can simplify no more. I'm at the end of my backward model reduction procedure, right? Because now all three variables are important to describe the ozone concentration. Should we just compare, didn't we do the wind, the temperature effect, say? 0.044, what was the temperature effect? I could maybe just copy it here. If I do like this, I copy this one down here as a comparison. I wanted to check the one that we already studied. Now I just redo it again, where I just take the temperature alone, right? Let me look at that one. Look at the quantification of the temperature effect. Here it's 0.06, plus minus something pretty certain. What was the temperature effect in the MLR model, multiple linear regression? Well, only 0.045, 044. It's a pretty different effect. It's positive, yes, but it's not the same effect. There is a smaller effect of temperature here in the MLR than in the first model. So that's how it is with MLR. The interpretation of the betas is to be seen relative to, or I mean, in the understanding of what else is in the model. So this is the interpretation of this temperature effect, is a temperature effect haven't been corrected for wind and radiation. So when I'm talking about this effect, it's comparing 2 days with 1 degree difference, but 2 days that have the same wind and radiation levels. So it's cleaned for, it's corrected for wind and radiation effects. Temperature is still important, even though I clean out the other effects, but it's a different effect, which we would expect. Why should it be the same? Because temperature, wind, and radiation are not completely independent phenomenon, actually. They sort of follow each other a little bit, and we don't have an exact orthogonal structure of those combined design information. We'll get to that later. So that's the MLR. Let's see. Model selection, I probably said the most here already. This is not a black and white science, I'm sorry. Model selection is a bit of an art. And with any art, it can be challenged. But we can compare with statistics, and in this course we focus on the backwards. The backwards is nice because then at least you don't do any mistakes in the beginning. Backwards can be challenged if you have really large number of x's and only sort of not so many observations. Then the large model could be a bit unstable in a way. So there's no sort of 100% clear answers to whether one or the other is preferable. For some situations one, for others another. Which variable would you remove first? What was that? Which one should we remove first? I'm sorry. Radiation, right? Sorry about that. I really hate. Oh, bugger. Let's see. But let's at least make make the other point then. There were two lucky ones in here. Anyway, some people need a bit of luck in life, right? So let's give them a chance. Now they're on the go for a new point in life here. You're in the game. You're a point to be made for the 13 red ones, just to not forget that one. Because there is a little point. I accept that the red one actually had the largest p-value. However, we never remove the intercept. Just leave the intercept in the model. That's not part of the game when we do model reduction. The intercept, I mean, it was not on the slides, but that's why I brought it here. The intercept is just something to make sure the plane is at the right position. We don't want to take that away. We don't want to force the plane into 0.0. Only in very rare cases I would discuss with the guy from physics or chemistry that if we have a meaningful model, we could force it through 0, comma 0, but most often just leave the intercept in. Never throw that away, right? That's the general rule. So, sorry about that, and welcome to Pineapple. It's a bit unfair, maybe we don't know what happened here, but anyway, sorry about that, and well, enjoy the break anyway. 15 minutes from now.